Let's take a quick tour of some phase diagrams which are technologically relevant. Let's start with the phase diagram for copper and tin. This copper-tin system is sometimes used in three-dimensional interconnects in microelectronic devices. To form the copper-tin interconnects, solid-liquid interdiffusion is used. And what happens is that you start with solid copper and solid tin at room temperature, and this is usually sort of deposited so that you have a layer of copper, and then you have a layer of tin, perhaps on top of another layer of copper, among other things. These are pressed together and heated up, and so this starts to react. And so if this is done at a temperature below the melting temperature of tin, which is relatively low, right, then what happens is that the copper and tin start to diffuse together, and the diffusion is fast in the tin because it's a high temperature relative to its melting point. And so within the tin phase, you start to first form this copper 6 tin 5 phase. And as the tin is consumed, if this is done basically with an excess of copper, you put a thin tin film, the tin is consumed and more copper starts to diffuse in, and you start to move further across this phase diagram, and you end up with the copper 3 tin phase, and that basically exists there. And then you can end up with basically a relatively stable, if you're over here somewhere, a relatively stable material where the tin has been incorporated into the copper at a relatively low temperature, even though it's a high temperature for tin, and you end up with phases which now have a very high melting temperature, right? So you've gone from a low melting temperature component over to these phases here, which have a relatively high melting temperature. So this is one way to sort of exploit our knowledge of the equilibrium state of a system to design something that we want. So let's look at another example. Our next example is the aluminum and nickel system. Aluminum nickel is important in high temperature alloys for jet engine turbine blades. These are usually made out of a nickel-based superalloy, so it goes beyond simply the addition of aluminum. But nickel and aluminum is an important binary system because we can understand a little bit where these alloys get their high temperature strength. So these nickel-aluminum alloys can be treated to have a number of very fine precipitates which inhibit the movement of dislocations, thereby strengthening the material quite a bit. So you can imagine if you pick an alloy with a composition somewhere around here. Okay, so somewhere around here. And you heat it up into this single phase region for what is called a solution treatment. And basically what you're doing is you're getting the aluminum alloys or the aluminum atoms rather, to dissolve in the nickel solution. So you have this solid solution of nickel with aluminum in it. And then if you quench this alloy, you get down here, and now you're really in a two-phase region, but your system has not had enough time to equilibrate, and so the aluminum is quenched in, and then you can heat this up to whatever temperature you want, well, to an appropriate temperature, and by controlling both the time and the temperature where this is done, you can precipitate out this Ni3Al phase. And if you choose just the right conditions, you can do it such that you have very many precipitates, but which are very small, and this adds the maximum amount of strength. So you start out with sort of an aluminum-rich well, not aluminum rich, but aluminum excess, right? So we have excess aluminum in this nickel solid solution. And what happens then is that you move towards equilibrium where you just have this nickel solid solution, but you can form a number of very small, so you want a high nucleation rate, but a low growth rate, so lots of tiny precipitates, and these are what then inhibit the motion of the dislocations through this. So the important feature here on the phase diagram is that we have a setup where you could find a solution treatment temperature where you can then go down into a single phase region, right? So this isn't always possible. We can't do this kind of precipitation hardening in aluminum using nickel, but we can do it in nickel using aluminum because of the sort of shape of the phase diagram. Our next example is the iron-carbon phase diagram. So here we have iron. You'll see this is only a very small section of the phase diagram. We can think about this even being sort of the iron and cementite, Fe3C phase diagram. Although it turns out that this cementite phase actually is metastable and doesn't always form. In fact, sometimes here instead what you get is just iron forming with graphite, which is what's way over here on the carbon end of the phase diagram. This is obviously very important because iron plus carbon is the basis of forming steel alloys and also for forming gray iron or ductile iron alloys as well. So some of the important things that we can notice on this phase diagram, iron is allotropic, so at low temperatures it has an alpha BCC structure, and at high temperature it has a gamma FCC structure, and then at even higher temperature it has one more BCC structure before finally melting. The gamma phase is what is the phase for many austenitic stainless steels. You'll notice that the solubility of carbon in the austenite phase is significantly higher than the solubility of carbon in the BCC phase. Depending on the amount of carbon which is added, you can make low carbon steel, and low carbon steel sort of happen on this part of the phase diagram. You can make a medium carbon steel, which goes up to about 0.6% C, or you can make a high carbon steel, which goes up to about 1.5% carbon. So this is a high carbon steel. For things like cast iron is usually with a higher amount of carbon, so cast iron is sort of more down here in this region, and fewer other alloying elements. And when cast iron is formed, the cementite phase doesn't form, but graphite forms instead, and so you can end up with either graphite sort of nodules, like little spheres, or graphite flakes, even in your cast iron. And that's a result mostly of the processing which happens at higher temperature in order to form cast iron, which is why the Fe3C phase isn't forming. We can look at one more example phase diagram which has some technological relevance, although the technology here is rather low-tech. So this is the phase diagram for water and salt, and so this is a weight percent salt. So here's pure salt, and over here is pure water, and so we see here the melting point of water. This is the liquid phase here, and it says brine because that's just the name for salty water, right? So this is the liquid. Down here we have basically ice plus water, salt mix, not water, but H2O solid. The interesting thing here, right, is that the melting temperature or the freezing point, right, we can think about this as the formation point of ice. So as we're cooling down at 0 C, ice will form. However, if you add in salt, you reduce that temperature. So here's our eutectic point in this system. So by adding salt, you can basically sustain the liquid phase to a temperature of negative 20 degrees C. This is important, obviously, because we want to melt ice on the road, right? We don't want ice on the road, we don't want ice on the sidewalk. And so by adding salt, we are decreasing that freezing point. And therefore, if it's negative 10 degrees outside, let's say, and we add salt, then we're going to go back to the liquid phase. So that's going to melt the ice. So this is the reason why adding salt onto the ice can reduce that freezing temperature and get the ice on the roadway to melt. So this is just a quick tour of some technologically relevant phase diagrams and how we can see from the equilibrium states on the phase diagram how these systems work and sort of provide some benefit to us.